Welcome everybody to the webinar of today. The speaker of today is Volfango Bertola, and he will talk about non-Newtonian drops. So as usual, I introduce the speaker very briefly, and then I leave him the floor. Professor Volfango Bertola joined the University of Liverpool in 2011, after holding a lectureship at the University of Edinburgh between 2004 and 2011. And a Marie Curie fellowship at the École Nationale Supérieure in Paris between 2001 and 2004. In 2009, between 2009 and 2010, he was a visiting professor and Lagrange fellow at Politecnico di Torino in Italy. He has more than 150 scientific publications in the areas of soft matter, multiphase flows, and thermodynamics, including several contributions on non-Newtonian drops and on the dynamics of wetting of complex fluids. He has been the recipient of a Royal Academy of Engineering Global Research Award in 2009 and UIT Young Research Prize in 2001. So it's with great pleasure that I introduced Volfango Bertola for his seminar of today. So Volfango, I stop sharing my screen and you can start sharing yours.
Okay, thank you, Francesco, for the very nice introduction, flattering introduction, and thank you all for having me today. I would like to tell you something about non-Newtonian drops. So we all know how important drops are in our everyday life. Just think of sprays in internal combustion engines. Depending on the size and distribution of the droplets, we can have a more or less efficient combustion, and so a more powerful or more energy saving engine. Most of the packaged food
sorry to interrupt you. You shall share your screen.
I did.
We don't see the screen at the moment. Yes. Yeah, that's
okay. So repeat, drops and sprays are important in our everyday life. We have internal combustion engines. Food, most of the food, the processed food, at some point in the production process involves spray drying to make powders. If you know a bit about turbo machinery, this is the effect of droplets impinging on the blades of a steam turbine. We have, of course, spray cooling, spray painting, more or less desirable. Sprays are extremely important in agriculture for the distribution of agrochemicals on crops. We have thermal sprays, and of course, we all know the importance of inkjet printing and inkjet manufacturing today. Sprays are common in nature. Think of the eruption of a volcano, or think of the foam generated by waves that hit cliffs, but they are also in the universe. Very often, the dynamics of galaxies can be modeled using hydrodynamic models, and very often they release droplets as they break large amounts of cosmic matter. They became more or less like liquid jets. We have a lot of sprays at home, including medical sprays when we are sick for drug delivery. And one of the beauties of studying these things is that we can span over large ranges of length scales and time scales. Go from molecular dynamic simulations, from molecular scales, then bit longer and larger scales when we study, for example, fluid dynamic singularities, such as the problem of the contact line and the contact angle in wetting. We can go to millimetric scales and milliseconds for the time scale when we study drop impact phenomena, and use even larger scales when we study sprays, which are the result of a combination of a large number of droplets. So how about drop impact in general? So imagine a droplet that hits a solid surface, a solid target. The first thing that happens is an inertial spreading stage. So the droplet, which initially is spherical, impacts the surface and spread more or less like a disk. In reality, there is a very thin layer, which is called lamella, surrounded by a toroidal rim. And this stage lasts for about 5 milliseconds. The second stage of drop impact has can have different outcomes depending on the conditions, first of all, of the substrate, on the roughness, on the wettability, porosity. And the second important parameter is the impact kinetic energy, or better, the ratio between the impact kinetic energy and the surface energy, which is expressed by the Weber number. So we can have, in general, roughly speaking, 3 cases. We have one case where the droplet just sits on the surface. We can have one case where the droplet bounces off the surface, down. And when the impact kinetic energy is very large compared to the surface forces, we have this case here on the right, which is called splashing. So the droplet breaks down into smaller satellite droplets. And how can we understand this in very simple terms? Well, the ground zero of any mathematical modeling is identifying the appropriate dimensionless numbers. So the simplest model of drop impact can be a spring dashpot system, where the elasticity of the spring is represented by the surface tension, because as we increase the free surface, for example, when the droplet spreads on the surface, we increase the surface energy, which is proportional to the area. And of course, damping, viscous dissipation is represented by viscosity. So, for example, if we plot the base diameter of the droplet, or the maximum diameter of the droplet, as it spreads on a surface, you see that at the beginning, it increases very rapidly. These are the few milliseconds of inertial spreading. It reaches a maximum. And then when it recoils, depending on the recoil velocity, we can have different outcomes. So if the recoil velocity is slow, the drop will just sit on the surface and take the shape of a spherical cap. If the recoil velocity is very fast, there will be enough energy for rebound, roughly speaking. How can we understand this in terms of dimensionless numbers? I already mentioned the Weber number that is important during impact, and this gives us the ratio between inertia and capillarity. But there is also dissipation, so we can take this into account through the Reynolds number defined based on the impact velocity. These two numbers are often combined together in the Ohnesorge number, which is the square root of the Weber number divided by the Reynolds number. And this contains both the viscosity and the surface tension. As for the recoil stage, in the recoil stage, there is one difference. The velocity is no longer the same. So we should use the recoil velocity, and the phenomena, the physical quantities that play a role are just viscosity and capillarity. So capillarity provides the driving force during recoil, because the droplet tends to minimize the surface, the free surface, so it becomes a spherical cap. And this process is delayed by the viscous dissipation. So these are the numbers we will play with. It is a very simplified description, but we can understand a number of things that are not so simple. For example, splashing. A very simple model of splashing can say splashing occurs if the dynamic pressure anywhere inside the droplet but near the surface exceeds the Laplace pressure. Okay? The dynamic pressure, of course, due to the velocity. So if we write this inequality in these terms, so for pressure, we take rho velocity density times velocity square over 2. We put a fudge factor, K, because we do not know exactly how much it is. And we say that this is larger than the Laplace pressure, so surface tension divided by an average radius of curvature of the surface, local radius of curvature, and we rearrange this system. We find that splashing occurs when the Weber number exceeds a critical threshold. And if you look into the literature, you will see that with some coefficients, the correlations to determine the point of splashes are all based on the Weber number or combinations of the Weber number and the Reynolds number. So even if we use very, very simple tools, we can understand more or less the trends of what is going on. There is something even more interesting when we have the impact of the droplets on a heated surface. So far we have seen the three basic outcomes of the drop impact: deposition, rebound, and breakup. These also happen on heated surface, but on heated surface there is something more. Because if the surface temperature is higher than the boiling point of the fluid, we have secondary atomization. We will see in a minute where the secondary atomization comes from. However, this can be superimposed to the basic outcomes, deposition, rebound, and breakup. And so we'll have deposition with secondary atomization, rebound with secondary atomization, and breakup with secondary atomization. And empirically, we can work out some maps that tells us where these impact outcomes happen depending on the impact Weber number and the surface temperature. So for example, rebound, dry rebound without any secondary atomization typically happens for low Weber numbers and high temperatures. While if we go to higher Weber number, we will have breakdown, drop breakdown, with or without secondary atomization. The origin of secondary atomization is essentially due to boiling, to nucleate boiling. So when we have the droplet on a heated surface, if the liquid is everywhere in contact with the surface and the temperature is above the boiling temperature, the boiling point, we will have nucleate boiling. Note that this can happen even in the case of Leidenfrost or semi-Leidenfrost droplets, when there is a vapor cushion that separates the liquid and the surface, because this vapor cushion, this vapor film may be unstable. So if locally the liquid of the droplet touches the surface, even for a very, very short time, we can have nucleation. And what happens is that these bubbles that are generated at the contact between the liquid and the surface rapidly go up by buoyancy, reach the free surface, and they burst. And in bursting, they generate the satellite droplets of secondary atomization. And these can be more or less strong depending on the impact Weber number, on the surface temperature, and so on. Okay, this is just an introduction to what we can expect to see when we have the impact of drops, any drops. But now we want to introduce to talk about non-Newtonian drops. And first of all, we want to remind what a non-Newtonian fluid is. as opposed to a Newtonian fluid. So as we know, a Newtonian fluid is a fluid for which the relationship between the stress tensor and the deformation rate tensor or velocity gradient tensor is linear. So an equation of this form. Anything else is non-Newtonian. So in a non-Newtonian fluid, the stress tensor can be a function of the deformation rate tensor, of its derivatives of any order, of the position and time. So you see that it can be very complicated. We use to think of Newtonian fluids in terms of the constitutive model that describes these Newtonian fluids. However, I want to recall a simple fact. There is no direct correspondence between a constitutive model and a Newtonian flow. Because what happens usually is the following. We have a certain fluid that does not behave like water or air. So we start to think about it. The first thing we do is we observe directly, eventually with the help of instrumentation, either rheometers or microscopic analysis of the flow structure under flow. Then we produce a mathematical model which results into our constitutive model. And you see that the weak point is here because the mathematical model can be more or less accurate. So a typical example is the power law model, which is used quite universally, especially by people who do simulations. And this model is clearly unphysical when the shear rates are very small or very large, because in one case we would have an infinite apparent viscosity, and in the other case we would have a perfectly inviscid fluid, so an ideal fluid. So we have to keep in mind that the constitutive model does not correspond to a real fluid. Another thing that we should bear in mind is we normally talk about non-Newtonian fluid, but the non-Newtonian behavior appears only when we apply a shear or we apply a force to the fluid. So when we have a flow. So the attribute non-Newtonian is for the flow, not for the fluid. We should talk about non-Newtonian fluids, flows and not of non-Newtonian fluids. But just a very, very picky. We normally sort non-Newtonian fluids into, or flows into, time independent and time dependent. Time independent can be the power law type fluids, so shear thinning, shear thickening. An important class is that of viscoplastic or yield stress fluids, and we have plenty of examples in the kitchen and the bathroom of these fluids. And then the trickier fluids to deal with are the time dependent, the so-called viscoelastic in particular, which require a very complicated constitutive model, which bring complications into the numerical modeling. So I will try in the rest of my talk to follow this more or less this classification and present non-Newtonian drops belonging to these four categories I have displayed at the bottom. I will start with the impact of viscoelastic drops on hydrophobic surfaces. And in particular, I am talking about dilute polymer solutions. Dilute polymer solutions are a very common fluid in a solution. Is below the overlap concentration, the shear viscosity remains low. It is can be 30 to 50% higher than the viscosity of the solvent, but it is not very high. So for example, if we have a spray generator, a nozzle, we can easily replace a solvent with a polymer solution without having to change either the pumping system or the nozzle. And the interest in drops of dilute polymer solution dates back to about 25 years ago for the distribution of agrochemical. So here on top we have two examples of drop impact. On the left, pure water. On the right, 100 parts per million polyethylene oxide solution with a very large molecular mass, by the way, 4 million. And you see that on the same surface with the same Weber number, the water drop rebounds and the polymer solution drop sticks to the surface. So the interest was driven by a company that was making agrochemicals. At the time, the name was Rhodia, and now it became part of the Solvay group. Because you understand that when you are distributing an agrochemical and you spray it on crops normally have hydrophobic leaves to keep away parasites and anything that can damage the leaf. Anyway, you want your agrochemical stays on the leaf. You do not want it to fall onto the ground to increase pollution and at the end to require more agrochemical to be distributed to obtain the same effect. So this was quite curious and hard to explain. So the first mechanism that was proposed to explain this phenomenon was that, okay, when I have a drop impact, I will have large velocity gradients in the droplets in a plane parallel to the surface. So these large velocity gradients will be able to stretch the polymer molecules. Polymer molecules are at rest in a coiled state to maximize the conformational entropy. If there are large velocity gradient, if it is a linear chain, this coil will unfold. What happens is that in a coiled molecule, the interaction between the fluid and the monomers occurs only on the surface of the sphere, or this spherical-like, sphere-like coil. If we stretch the chain, the interactions will be with all the monomers of the chain, and this increases friction. And this traditionally is represented using the concept of elongational velocity. So the ratio between the first normal stress difference and the elongation gradient. And usually it is given as a multiple of the shear viscosity. And this coefficient is called the Troughton ratio, which for a Newtonian fluid is exactly 3, because in a Newtonian fluid, the only normal stress is pressure, essentially. And in a non-Newtonian fluid, in a polymer solution, can be 3 orders of magnitude higher. Okay, dissipation. So there were quite a lot of studies investigating these correlations. There was a Boger's group in Australia who did a lot of transient elongational viscosity measurements for different fluids. You see that these measurements are not only tricky, but the error bar is quite large. However, they managed to correlate quite clearly both the recoil velocity of polymer solution drops and the rebound height with the Troughton ratio, so with the elongational viscosity. So at some point, the bouncing height becomes 0 if the elongational viscosity is high enough. Okay, fair enough. And they also took high-speed images. Here you can see clearly that as you increase the molecular weight of the polymer, so you increase the relaxation time, you increase the elongational viscosity, you see that at some point the drop does not bounce anymore. So all good. Unfortunately not, because the fact that two phenomena are correlated, so they appear simultaneously, does not mean that there is a cause-effect relationship between each other. And in fact, there were a few issues with the elongational viscosity. The first issue was highlighted by a series of experiments done in Marne-Vallée in the group of Michel Vigne-Sadler. She studied the impact of the polymer solution drops on small targets, on very small targets. So these are images, views from above. You see the white spot is the small target, and the film around it is the spreading disk of the droplet. So they measured the spreading ratio, so the diameter versus divided by the equilibrium diameter of the droplet versus time, and they found that water and polymer solutions have exactly the same spreading ratio during time. So, wow, water has no elongational viscosity. The other drops do have a large elongational viscosity, so probably it's not the elongational viscosity. There are other experiments that go against this interpretation, and these are experiments done on Leidenfrost droplets. So the case I mentioned before, where the droplet does not touch the wall because there is a vapor film in between. So this is a clear animation, but what happens essentially is this. If the surface temperature is sufficiently high, the vapor film forms almost instantaneously, not instantaneously, but almost instantaneously. So the liquid is never in contact with the surface. And if we compare water drops and polymer solution drops impacting on a heated surface, what we see is that, so in these figures, the open symbols are water and the filled symbols are the polymer. The maximum spreading diameter is slightly smaller for the polymer solutions. Makes sense because they are a bit more viscous, so if they spread a bit less, it's okay. But then the bouncing height, especially for high Weber number, is the other way around, as it should be. So the polymer drops bounce higher than the water drops. So here, if we assume that the bouncing height is due to the elastic energy stored by the polymer, turns out that here we have a problem with energy conservation. That's the only possible answer. So there was another issue with the elongational viscosity, which came from an infamous lab in Paris. The problem was that the elongational viscosity measurements that were used to propose initially the interpretation of the absence of rebound in terms of elongational viscosity were this. So the graph on the left, this was the first paper to talk about the anti-rebound effect of a polymer solution. The thing is, a few years later, the same group republished the same data for another purpose. If you take the time to read the caption, you will see that they are exactly the same fluids, done with the same molecular weights, the same concentrations, etc. And if you put the two graphs one over the other, you see they not overlap. And okay, you see this point, the distance is not large. It is because it's a logarithmic scale. If we plot one measurement versus the other, we see that the points that are not aligned, that are not okay, have a difference of 100%, so factor 2. And they are only on one side. So if it was an accidental random measurement error, I would expect that they would be distributed on either side. So here there is everything that makes a physicist happy. Quantum measurement error, is it 0 or 1? And symmetry breaking, because it's going on one side. So overall, there was something strange. And what we did then to try and understand what was going on, we decided to measure the velocity field inside the droplet, because that's the only way to understand whether you have sufficient velocity gradients, because when you have the velocity field with respect to time, you also have the velocity gradient. And to do so, we used a quite weird setup. So we had an inverted microscope to visualize the target of the droplet from below. We illuminated the field with a pulse laser at a certain frequency, and then we sampled the impact with a high-speed camera at 1/4 of the frequency of the laser. So basically, if we seeded our liquid with a fluorescent particle, on each image of the camera, we would visualize the same particle 4 times. So we could follow it along the trajectory. Because for one frame, we would have 4 flashes of the laser illuminating it. And during time, the particle would move, so we would see the same particle at 4 different positions. So this had 2 advantages. First, from the distance between 2 particles divided by the delta t, so the reciprocal of the frame rate, we had the velocity. And by collimating the directions, the trajectories of different particles, we could identify the drop center, right? And so we had the radial position of the frame we were analyzing. Because with a microscope, you cannot visualize the full droplet in the field of view. And the results were quite interesting, because they say that within the droplet, the velocities were identical, velocities and velocity gradients over time. Of course, the data for the water drop, due to the slightly lower viscosity, are a bit more blurry, erratic, let's say. The error bar is a bit larger, but if you look at the scales, the orders of magnitude are exactly the same. And the first part of the curve is for the spreading stage, so positive velocities. The rest is for the recoil. So even during the recoil, the fluid in the water drop and in the polymer solution drop have the same velocity. Same velocity gradients. And therefore, why do we see the polymer droplet when we visualize it with our eyes? We think that it is lower, because it is the contact line. So in these 2 movies, we have, again, one water droplet on the left and the polymer solution droplet on the right. On the graph on top, the black points are the velocity of the fluid inside the droplet, and these 2 white points are the velocity of the contact line. So it is the contact line that moves much slower in the polymer solution, while the rest of the fluid in the bulk is the same. So the question now becomes, is it elongation of velocity, or since it is the contact line that moves slower, is it just a problem of wetting, as suggested by the Leidenfrost experiments and the impacts on small targets? Well, we can look at the contact angles. Again, water on the left, water plus polymer on the right. You do not need to measure the contact angle. You can just see with your eyes that the contact angle for the polymer solution is much smaller than the contact angle of the polymer drop. And so from this set of experiments altogether, we can quite confidently say that it is not a problem of rheology, of elongational viscosity, but it is a problem of wetting. And so we can do something more. We can look at the details microscopically of the contact line. Can you see this video, or shall I play it again? Because it's a bit dark. You see that the contact line, as it moves backwards, leaves behind some filaments, some stretched filament. Now you see these brighter points, brighter spots. These are droplets resulting from the breakup of the filament. So there is this polymer solution filament that is stretched by the receding contact line. At the end, it breaks down into a lot of smaller droplets. Do you remember this famous, very famous paper by the group of McKinley, the beads on a string? They had the filament of polymer solution in elongational flow, and it made like a number, several beads or pearls on a string. This is very similar. However, the difference here is that the filament sits on a surface. So it's not an elongational flow, it's shear flow, because it is wall bound. Some image processing to highlight the beautiful structures. And we see that if you have pure water, so 0 ppm concentration, the contact line is just smooth. But as soon as you add a bit of polymer, as low as 40 ppm, you start to create these filaments or threads when the contact line recedes and sweeps the surface. We wanted to make sure that there was a polymer in this filament, and it was just not water. So instead of using just a synthetic polymer like PO, we added a small amount of fluorescent DNA, because it's the easiest thing to visualize. And in fact, if we look at the substrate, just after the transit of the receding contact line, we see these fluorescent lines, which have a length scale corresponding to the length of a fully stretched DNA molecule. So we are quite sure that these molecules are stretched, but only near the contact line because of the sweeping of the receding contact line on the surface. Okay, but these are just qualitative experiments, if you wish. Can we do something more? Well, we can, provided we poke a bit of thermodynamics and we take it with a pinch of salt. So at equilibrium, we have the Young-Laplace law, and I think this is fine for everybody. When we are out of equilibrium, the contact line moves, and we cannot really use the Young-Laplace equation because this comes from the minimization of the free energy. We cannot do when we are out of equilibrium. However, someone introduced the concept of line tension. So if the contact line moves, it means that the surface force has a smaller angle with the surface. So the receding contact angle is smaller than the equilibrium contact angle. So its projection in the direction of movement is higher and is able to balance the solid vapor tension, which pulls the other way around. So the idea here is, since we cannot write an equality for thermodynamic reason, we imagine that there is this line tension, which is a force per unit length, pulling outwards. And in this way, we can balance the additional recalling force due to the smaller contact angle. So we said, okay, if we use this approach, which is not very rigorous, but it's okay, and we have the polymer, we can imagine that we add on top of the line tension a force per unit length due to the polymer. Stretching of these filaments will tend to pull the contact line, and so it moves slower. But how can we calculate the polymer force, more or less? Well, we can go back and take the old basics of the Fini model. So there is the initial article of Bertola, which determined the force of a single polymer molecule, and this L is a kind of arbitrary function that changes steeply across zero. You can imagine it as an arc tangent. And it is a function of the fractional elongation of the droplet, which was calculated by Dejean in the famous coil stress transition paper. It is a bit tricky because, as you see, it is an implicit equation, but numerically we can solve it. And multiplying by the expected number of molecules, which depend on the polymer concentration in the droplet, etc., we end up that we can calculate the force of the polymer per unit length. And here it is represented normalized with respect to the surface tension of the liquid. And we see that this polymer force is a significant fraction, I would say it's of the same order as the capillary force. So it is sufficient to delay or even stop the recoil of the droplet because it has the same magnitude as the capillary force. This, I think, provides a reasonable explanation for the behavior of droplets containing small amounts of polymers. I want to show you now something quite amusing, which is the effect of these polymer additives on the impact of droplets on heated surfaces. Because we have seen the morphologies are quite amusing. The first thing polymers do is that they prevent splashing. So on the left, you see a water droplet impacting on a certain surface with a certain Weber number. And on the right, same impact condition, but with 200 parts per million of PO, the first droplet breaks down, the second doesn't. So one conclusion we can say is polymers in small concentration can significantly increase the threshold Weber number for droplet breakdown. Okay, can be useful. They change always the morphology. So here we have a case of rebound with a single satellite droplet that goes away. If we repeat the experiment with the polymer solution, we see that satellite droplets tends to go, but then there is a filament that remains and pulls the satellite droplet back into the main drop. Another thing polymers do is they suppress completely secondary atomization. So you see, on the left now we have the water droplet. It starts to boil. When it starts to boil, you see the satellite droplets going all around very quickly. The polymer solution droplet will boil. You will see some movement down. The quality of these movies is not great because they are very old. However, you can see on the right some boiling, but satellite droplets do not depart. And imagine this is not a trivial problem for applications, because we had issues of trying to inkjet print metals to make microelectronics, to make electronic interconnections. Metals are printed usually in suspension in an organometallic solvent. So the organic part evaporates upon deposition. But in order to evaporate quickly, they need to be printed on a heated surface. So if you want to print a very fine track and you have secondary atomization, the metal will be distributed at a certain distance from the track. And so the quality of that electrical connection will be very poor. It will not work. So this was very useful to address that issue. We can see it even better here when we have secondary atomization upon impact. So this is a Leidenfrost drop that bounces because of the vapor film, but before, since the film is not stable, it sprays droplets. And with the polymer, this doesn't happen. So same condition, same surface temperature, the drop will just bounce off and no satellite droplets. So in quantitative terms, the Leidenfrost temperature for Newtonian fluids increases with the Weber number. Because if we have a higher Weber number, the vapor film is pushed down, okay? It tends to become thinner, and so we will have contact between the liquid and the surface. If we have the polymer solution, the dynamic Leidenfrost temperature remains independent of the Weber number and almost identical to the static Leidenfrost temperature. Other funny things. Did you see anything in this movie? Probably not. If we isolate single frames, this is a case where the Newtonian drop would have secondary atomization. You see the satellite droplets here that tend to depart, but there is the liquid bridge that pulls them back. So that's how secondary atomization is suppressed in polymer solution droplets. And again, do you see anything here? This is a droplet that in normal Newtonian conditions would splash, would break down. But analyzing the frames, you see the satellite droplets around the rim tend to leave, but there is always this liquid bridge that over time pulls back any loose droplets that want to break down. So it is quite interesting, and you can put all together this effect and study a bit the effect of the relaxation time. You can change the relaxation time either by increasing the concentration, like in this case, or by increasing the molecular weight of the polymer. And in either case, the result is always the same. Breakup and secondary atomization are killed. So on the left maps, we have a variety of morphology. On the right, everything is suppressed, and you have either the rebound or simple deposition. That's it. So this is the effect of polymers on droplets impacting on heated surface. Something a bit more interesting, that was just qualitative, is studying the problem of the viscoelastic Leidenfrost droplets, because we have seen it helped us to understand the problem of the impact and rebound on a hydrophobic surface. But still, there was this issue with the energy conservation that was not really sorted. So just to recall, the droplet of polymer spreads a bit less than the droplet of water. However, it rebounds higher. So where does this energy come from to bounce higher? So we try to use different fluids. We used, again, water with a certain viscosity, elastic polymer solution with a similar viscosity, and I say, what happens with a shear thinning fluid? The shear thinning fluid should spread more, right? And so bounce a bit less, because in spreading it would dissipate more. The result was the shear thinning fluid, despite having a much higher shear viscosity, was bouncing higher than the other droplets, even of the elastic droplet. Okay? So one droplet is elastic, I would expect it to bounce higher. The shear thinning droplet has no elasticity apart from that of the surface tension, and still goes higher. Measured it systematically, you see that as the Weber number increases, so this happens for large Weber numbers, large impact kinetic energy, we have the shear thinning droplet rebounding 5 times higher than the water drop in the same conditions. Wow. So we thought that the only way to try and understand what was going on was to create a system that was really comparable. So we built by trial and error, and trial and error translated into about 1 year of errors, to make fluids with matching flow curves. So we used xanthan, which is a known shear thinning fluid. So as we increase the shear rate, the apparent viscosity decreases. And then we matched this flow curve with a polyacrylamide solution, just tuning the concentration very, very finely. The polyacrylamide is a polymer that has both shear thinning and viscoelastic properties. So with this system, and then we took glycerol solutions to match the infinite shear rate and zero shear rate viscosities of these flow curves, calculated using a Carroll-Yasuda model extrapolation. And we repeated the measurements, and we saw that more or less the bouncing height was the same for all fluids except the Newtonian fluid with the infinite shear rate viscosity. So we started to restrict our focus, our area of investigation. And at the end, we found that the droplets that jump low, that do not jump high, rotate during the rebound, while the other droplets keep their symmetry and have no rotation. So we suspected that it could be the kinetic energy lost or required by the rotation. And so we made a very rough estimation of this kinetic energy. We assumed a shape of the droplet, for example, a rod or an ellipsoid, to have the correct moment of inertia. And then we converted this energy into a height, into a potential energy. And we corrected the charts of the bouncing height with this extra height due to the kinetic energy. And magic, the bad points, so the triangles, which were much lower, started to agree with the other points. So we found that the reason why there was this bouncing height different was due to the fact that the low viscosity droplets have this rotation. Okay, but then the other question was, why do these droplets rotate? And we understood it by comparing droplets around the maximum spreading diameter. So these are different fluids. So at the bottom, we have Newtonian fluid at zero shear rate viscosity, so high viscosity. Then viscoelastic, shear thinning. And we see that at maximum spreading, they do not really have a rimming stability. They do not tend to form satellite droplets that are the precursor of splashing. But the low viscosity fluid does. So they have this crown of satellite droplets that for higher impact kinetic energy will just scatter around and cause droplet breakdown. But at moderate impact velocity will just recoil with the rest of the droplet. The problem is exactly in recoiling, because we all know that when we have a disk under compression, we have instabilities. The same happens to the droplet. And therefore, due to this instability, we may have that two of these droplets, two or more, coalesce. In coalescing, they break the cylindrical symmetry of the droplet and they change the mass distribution. So the mass distribution is no longer homogeneous in the disk, but there are some points where there is more liquid and some other points where there is less liquid. And this is sufficient to create the moment of inertia when the droplets takes off and leaves the surface. And so that's more or less everything. But there are other interesting droplets that have non-Newtonian properties. For example, the viscoplastic droplets. So these droplets that for low applied stresses behave like solids, and above a certain threshold of stress start to flow. The first thing we noticed that when we tried to generate them from a needle or a nozzle, they were not spherical. Or better, they were not spherical except when the yield stress was very low. So we characterize it with a geometric parameter. If it is this parameter is 0, the drop is spherical. If it is larger than 0, it's not. And we measured it for droplets during free fall to see if they recalled the droplet to the spherical shape. Above a certain value of the yield stress, the drop remained prolate forever. But we introduce a number to characterize it, which is the product of the capillary number and the Bingham number. The idea is when we have a droplet of a yield stress fluid, we have two forces in competition. We have the capillary force or the Laplace pressure, and we have the stress, the yield stress. So if the capillary force is larger or significantly larger than the yield stress, then we can deform the droplet. If the yield stress exceeds the Laplace pressure, the droplet cannot be deformed, behave like a solid. And in fact, if we plot the shape factor, the parameter that tells us if the droplet is spherical or not, we see that it matches very well with this definition of Bingham capillary number, because the droplet remains spherical or becomes spherical only up to a value of this number equal to 1. Above, we are in a viscoplastic regime. It means that the yield stress exceeds the Laplace pressure, is higher than the Laplace pressure, and so the Laplace pressure cannot recover the spherical shape of the droplet to minimize the surface energy. Okay, this is a simple example, but it is used also for another thing. Here I'm showing two examples of viscoplastic droplets. So low yield stress on the left, and it looks like a Newtonian droplet. On the right, we see that there is a part that remains not deformed in the center. And this is due to the fact that in the center of the drop, the stresses are lower because the radial velocity is lower, so the velocity gradients are also smaller. And so there is this part that remains not deformed. Another interesting feature, en passant, is that the spreading ratio, so the maximum spreading diameter, changes with viscosity. Okay, if we increase the viscosity of a droplet, the maximum spreading diameter reduces because of viscous dissipation. But in Newtonian drops, it reduces as a power law. In yield stress drops, it reduces linearly. I have no idea why, just an experimental observation. Oh, and of course, you can play both with the yield stress of the fluid and with the Weber number. So depending on the Weber number and the yield stress, you can have a range of final shapes of the drop, which can be useful in manufacturing to create patterns on the surface. So this could be, for example, with the appropriate nozzle and appropriate inkjet printer, an easy way to fabricate superhydrophobic surfaces. When we have a bit higher yield stress, we have just a plastic deformation and virtually no rebound. So again, the capillary force cannot recall the spherical shape. Because of that, we have a disk-like droplets or a pancake on the surface. And again, it is very well characterized by the Bingham capillary number. Something even more complicated is the impact of a viscoplastic drop on a viscoplastic surface. This is interesting for inkjet printing because when we add a layer of material on the previous layer is the same material, but partially cured or dried, so it is a bit harder. So we wanted to understand what happened to the droplet of this on this surface, how the material of the droplet, the fluid in the droplet, would diffuse and merge with the material of the substrate. These experiments are a bit tricky because you have a change of refraction index when the droplet penetrates into the viscoplastic liquid. And you have the layer of material of the droplet that is distributed on the surface of the crater that is created by the drop penetrating into the gel. And then the distribution of this material changes depending on the condition. So we studied this, and by more or less complicated digital image processing method. So we were able to distinguish the substrate, the drop fluid, and the crater, so the empty space. And we changed both the yield stress of the droplet and the yield stress of the surface. An interesting thing we noticed is that on harder surfaces, so when the surface has a tougher yield stress, the drop tends to penetrate more deeply when we increase the Weber number, which makes sense. However, when the surface is softer, so the yield stress of the surface is lower, the droplets tend to spread more as we increase the Weber number. So the material tends to stay on the surface instead of penetrating into the material deeply. And we could work out a sort of correlation. We found that in some cases, the droplet is fully absorbed by the surface. So when the crater disappears, the surface is flat and all the droplet has been incorporated into the substrate. In other conditions, which depend both on the Weber number, so the impact kinetic energy, and the ratio of yield stress between the droplet and the surface, in other conditions, only a part of the droplet is absorbed by the substrate and remains below the surface, and the rest forms a kind of bump over the surface. This is just out of curiosity. I want to finish with a very interesting fluid, which unfortunately is not very studied because it is difficult to deal with. And this is a shear thickening fluid, or better, a jamming fluid, which is made of a concentrated suspension of particles. So here we use the model system of very small particles, 600 nanometers diameter, which behave more or less like hard spheres. And we use the concentration of around 60%, which is close to the maximum random packing concentration of particles in a given space. And we used a fluid, a solvent with a very high boiling point. So we ensured that there was no evaporation in ambient conditions. So the behavior, the ecology of this suspension is bizarre because they look like liquid. So you see that the surface is gloss, so they have a liquid-like behavior. But if they go under large deformation gradients, large velocity gradients, like in a uniaxial extension, they become brittle. They are strongly shear thickening. You say they are jamming. So the particles are blocked in a cage with respect to one another. So there cannot be a continuous deformation like in a fluid. But if you see effectively, they break up like a solid. You see the fracture occurs at 45 degrees, so in the direction of maximum stress. And the flow curve is also interesting. It is a shear thickening fluid, but if we model with a power law, we see that it is broken. The flow curve is broken into two branches. So the low branch here is when the fluid behaves like a liquid, and here is when it behaves like a solid. So we have a very large increase of shear stress when we increase of a small amount the shear rate. So how do these droplets behave? When they impact a hydrophilic target, like a glass, no matter of the Weber number, instead of spreading upon impact, they remain jammed, they block, because there is a large rate of deformation upon impact, so the particles jam, and we do not have the inertial spreading. So if we plot the base diameter versus time, where we should have maximum spreading, so after 5 milliseconds, we see that the base diameter has remained the same. And then, because of capillarity, slowly the droplets start to spread, and the base diameter grows. If we repeat the experiment on a hydrophobic surface, there is still jamming. The drop remains blocked. The shape tends to rearrange and become spherical with time, but the base diameter does not change, remains constant. And when I say constant, I really mean constant, because a few weeks later, now let me get rid of this if I can, a few weeks later, the drops are still there. We even released one drop of top of another, just to see, and weeks later they had kept the same shape. They had not spread, they had not deformed. So we believe that this is due to the fact that once the system is jammed, you need some action in order to dejam the system. And in the case of the hydrophilic surface, this action is due to the capillarity. So the solvent will tend to wet the surface, so it will tend to move. In doing so, it will push some particles, just a few particles, out of their position, and this is enough to give the onset of a kind of cascade, of a kind of avalanche that releases all the other particles that were frozen, that were jammed, and enable spreading. If the solvent is not allowed to spread because the surface is hydrophobic, there is nothing that can dejam the system, that can pull the particles out of their position. And that's why the system stays permanently in this state. However, this requires some further investigation. Bon, j'espère que je vous donne une idée de la beauté, de la diversité, mais aussi de la complexité du sujet des groupes non-newtoniens. Et voilà, je vous remercie beaucoup pour votre attention. Et je m'excuse pour l'accident.
So thank you, Volfango, for the very interesting and detailed talk. So I would say let's see if there are questions in the room. I don't see the camera, so you can tell me if there are some people in the room who want to ask a question.
You didn't mention, you mentioned sometimes, not involving your explanation of temperature at all. I assume that when you had the problem of wetting with the contact line, temperature probably plays a role in some way. For example, when you said the polymer and the capillary force are the same order, is it for any temperature?
Yes, I didn't mention the temperature because all the study is on homo-thermal temperatures. Right? That problem is only at ambient temperature. So surface and droplet at the same temperature. On heated surface, I have no idea.
So
on heated surface, there is another issue. You can have a pyrolysis of the polymer. So
if it's homogeneous temperature, as you said, if you change the temperature a lot without having to go to extremes, is they the same? This temperature has a small effect?
but are you speaking about the recoil velocity?
Yes.
Yes, it does. However, again, this is something observed. You need a hydrophobic surface to look at this, because you want a nice recoil. You do not want a wet thing. Okay, so you need a recoil. But to have a heated surface, usually you have a metal, and the metal is a hydrophilic. So they really do not match very well. But yeah, why not? In theory, one can figure out an experiment. No, something on top of my mind, a metallic substrate coated with PTFE, the spray PTFE. And as far as I know, there is nothing in the literature as well.
Okay, so are there other questions in the room?
Maybe I have one question. You mentioned that at one moment that you measure the velocity inside the droplet, and how is it possible? I mean, you see the droplet by.
So I was a bit quick. Okay, here we are. That's how we did. So the droplet was impacted on an inverted microscope. Right? So we were looking at the flow field from below, seeded with fluorescent particles. So that's a particle tracking technique. The illumination was at a frequency 4 times the sampling rate of the camera. So in each frame of the camera, we were seeing the same particle 4 times. So obviously, since the velocity is radial during the spreading and initial stages of recoil on a plane, the distance between 2 images of the particle divided by the delta t gives the velocity of the particle.
The seeding is very low, so that it doesn't affect the property of the.
Yes.
Oh.
So no PIV, just PTV. And then the 4 particles allowed us to draw the trajectory. So we had a radius. If we took another particle, we had another radius converging, so we could determine the distance from the drop center. So we also had the position, because with the field of view of the microscope, it's impossible to see everything. So yes, we had the measurement, but we didn't know where. So.
I have a quick question about creative jobs. When we trying to creative a job, how can we control the size of the job? I tried before in some experiments that it's not very matched with the diameter with the needle.
But depends. It depends on the fluid.
Yeah.
So if you have generally a low viscosity or low yield stress fluid, you can generate the drop from a needle, and the size is determined by the surface tension, always. And if you want to have a precise idea of the drop size, what you have to do is weighing the droplet, because from the weight, you know the volume, if you know the density of the fluid, of course. From the volume, you have the diameter. So if you make a statistics over 50 or 60 droplets, you have a quite accurate measurement of the droplet, meaning that you know that needle with that fluid will give you droplets of that size. If you want more accurate droplets, you have to ask someone who is good with his hands to make, for example, an ultrasonic nozzle or a pressure pulse nozzle. So you can deliver an exact volume from a nozzle using a membrane that receives a piezoelectric or another form of pulse. And that's what they do in the print heads of inkjet printers.
Okay. Are there other questions in the room? Then maybe I can ask you a question, Volfango, maybe a couple of them. Actually, one is about the phenomenon you showed before, related to viscoelastic recoil, that basically the wetting. Yes, correct. In this case, I mean, a modeling approach would be to model the fluid, as you mentioned also before, as a viscoelastic fluid with a certain extensibility and so on. But would polymers interaction, so the interaction between polymer chains eventually affect this phenomenon, and that would not be captured in the model, right?
I answered the first question. The first answer is no, because we are in the dilute regime. So in the dilute regime, molecules do not overlap, meaning that the average distance between two molecules is much larger than the radius of gyration of the molecule. So they are far away. Like I say something very inappropriate, like an ideal gas. They're far away. And it is the concentration is very much below the overlap concentration. So they do not even get very close.
Okay.
In fact, we can really talk about individual molecules in a solvent. But the problem is, how do you model this?
Yeah, exactly. That's that was my point. Yeah, in this.
No, I think there you have to go down to mesoscopic modeling.
Yeah, because I mean, you don't have anymore the hypothesis of dilute solution in this case. Yeah.
That's another thing. How do you know, or how can you verify experimentally whether in the corner near the contact line your actual concentration, local concentration, remains the same, the bulk drop, or changes?
Yeah,
because you have the receding contact line. So if you imagine someone sweeping a room, all the rubbish accumulates near the sweeping broom.
Yes.
And so I guess that the polymer molecules accumulate near the contact line. And that's why you have this strange effect that would not be there in a dilute solution. Because in a dilute solution, you cannot make the bead on a string experiment.
Yes. Yeah. Okay, thank you. And I do have another question on the last fluids you showed, that they were jamming. Yeah, they were jamming, and in this case, you described it. You described the effect of capillarity at the end when you talked about the two different substrates. You described the effect of capillarity, and is it like, are you using a sort of thinking system that looks like that's trying to model this sort of fluids like a granular medium? Basically,
no, and there is not much again because of the jamming. Because when you have a jamming, you have a more or less sharp transition, and it will blow up any CFD models based on a continuum approach. So there was something, my kids started to do some modeling of this, but honestly, I haven't followed the literature for a number of years now about this.
Okay.
What can I say is that this part of the curve, so when we have the spreading, can fit very well with the spreading model for shear thickening fluids. So if we plug into the drop spreading model the coefficients of our constitutive model,
yeah,
we find a pretty good match.
Okay. Okay. So this suggests that can be at least captured phenomenologically by thickening of the fluid. Yeah. So
the spreading, but the problem will be the jamming.
Of course. Yeah. Okay. Thank you. So you can tell me if there are other questions in the room, and if that's not the case, just last chance.
I think no, but in any case, I will hang out now for a while. So if there are any questions, you can ask me outside.
Okay.
So no questions in the room. They're bored enough.
So thank you very much for the very interesting talk and this overview of non-Newtonian drops. I invite our audience to thank our speaker again, and thanks once again, Volfango.